Welcome to the channel, everyone. This is Jonathan with Wild Arms Research and Development. It's been quite a while since we did a update video for the Swizzle Stick Hypervelocity rocket. To recap, this project is recreating a 1960s era, very lightweight hypervelocity rocket that relied on kinetic energy rather than explosive reaction to penetrate targets. So the average rocket motor is typically has a length to diameter ratio of 10 to 20. That is pretty standard. A lot go shorter than that. This one used a length to diameter ratio of 40, which is incredibly long. And that creates a lot of challenges. Primarily, the challenge comes with erosive burning, a high initial peak pressure, oftentimes will damage the rocket motor because of that peak pressure of all that surface area inside the rocket grain. Because it's so long, it's just too much to handle for most rocket motors. So that is what our project is about, is to recreate this rocket and solve that problem, which the original did solve, mind you. We are currently purchasing rocket propellant grains and coring them out to the size that we need. This is down to a couple variables due to limited time myself. I have not had the opportunity to pour a new batch of propellant. This saves a lot of time as well as it reduces a variable. While I've made a lot of successful batches of propellant, I am still learning. So it is possible that I ruin a batch, and I don't want that to be a part of a variable when we're trying to reduce the amount of variables and try to perfect the science of making a high length to diameter ratio rocket motor. With those rocket components created, we have now been working on the propellant side of things and developing the inhibitor, which the inhibitor is a coating or a restrictor on a propellant grain surface that prevents the flame from reaching that propellant and preventing or delaying the burning of that propellant. That's very important for designing a high length to diameter ratio rocket motor. There is a lot of science to it. Our first batch of inhibitor, we used HTPB, which is the binder in the propellant. But we had, in our design, we used too much carbon black. We were copying a patent from Thikel, and that mixture was just far too thick to be applied to the rocket motor evenly. So we decided to core out this propellant, fill a caulk gun with we'll call it black goo. We filled the propellant grains up, let them cure, and tried to re-drill out a core, a smaller size core, and that way the idea was to have an even layer of inhibitor on a certain amount of grains in this rocket motor. When we would try to drill it, the drill was struggling to go through, and it would start ripping the inhibitor off of the propellant, and that's a big problem. So we are revising that. We're doing more research into different formulas. I think we found a formula that's going to work. And instead of filling an entire core of propellant with this, I think we're going to be looking at dipping the propellant in this time. On the other hand, we also were working to copy the original, which used aluminum shields that were bonded to the surface of the propellant. And that method would work pretty well if we were pouring our own grain, but we were coring out existing grains and then trying to apply it post coring. And that did, when we pressed it in without any binder, it worked great. Once we started adding the binder to the rear of the aluminum to press it into the grain, that's when we started getting issues of the aluminum crumpling. And now this is not your standard aluminum that you'd get at the grocery store. This is much thicker. I believe it was around 200 microns thick. So it is bendable, but it also is pretty firm. But with the very tacky HTPB, it just started crumpling, or it didn't evenly distribute the HDB along the length of it, and it would just crumple, and it'd be raised in the middle. It was very difficult to get this setup to work. So I think we're going with the HTPB binder mixed with a filler and then some other catalysts and curing agents, and using that method. I think that's much better suited for the application of pre-poured grains that we have a lot of. If we were going to make our own propellant, we would stick these aluminum shields on the mandrel, pour the propellant around it, and when the propellant cured, you would have those aluminum shields along the entire length of the rocket motor, and that would work pretty well. And what I'm sure everyone's here to see is our first test, is our control sample. While we were working on this inhibitor, I created enough grains to be able to make an entire rocket motor without any inhibitor at all. To really know what would happen if there is no inhibitor on the propellant grains, we didn't have high hopes that it would survive, but according to our open motor simulation, in theory, it could have worked. But erosive burning is very hard to predict and control, especially with no inhibitor. The simulations were not going to be accurate compared to doing shorter length rocket motors where erosive burning is not a factor as much. And I wanted to give a special thanks to Mr. Snow Makes, Hank the Shank, and my rocket mentor who's been helping me, Tim.
So we're hooking up the igniter for the swizzle stick hypervelocity rocket. What can you tell me about that, John?
This is a 1-inch diameter by 40-inch rocket motor. The goal is to get up to 5,000 feet per second. This is the first static test to test the hardware. We're not recording thrust or anything, we're just getting the data from whether it explodes or not. Live, and we are going to get to a safe location.
Run away!
Okay. Swizzle stick test in 5, 4, 3, 2, 1.
First post-action report, how do you feel?
Well, no one got hurt, so that's number one. Second, as Tim was saying, that we reached full pressure. The motor case failed from the looks of it.
Yep. The place sand was an excellent safety device.
Yes.
Here's the other rupture. It looks like right about 75% of the way down the case.
Yeah. Pretty hot, but we see a little bit of cracking here, so we may just need to use a stronger carbon fiber. We also need to inhibit the propellant grain to delay that ignition. Yeah, it's really hot. Did it break? It broke in 2 spots.
Yeah.
As you can see, that was quite the spectacle. Luckily, everyone was safe. We set everything up in a way that would, if it failed, it would not impact anyone and everyone was at a safe distance. So that is number one. While disappointing that this rocket exploded, it wasn't unexpected. This is the control sample, so we were kind of expecting it to blow up. This was great practice for future tests. We were able to test a lot of our static test stand. We were able to see how our hardware and nozzle would perform under these kind of extreme conditions. We were able to see how the sand would work at containing the explosion for future tests. We were able to see how the welding mats would hold up to high temperatures. That is that was in front of the nozzle that prevented grass from catching fire. Uh, at the end of the day, we learned a lot of new information, and we are better prepared for test number 2. And hopefully, it doesn't explode like this one did. But that was the whole point of using an inhibitor, is to make this type of rocket possible. If you wish to support us, please pick up a copy of one of our books on Amazon. It'll be linked down below. We are not sponsored by anyone currently, so this will make it possible for us to continue building rockets. Thank you and have a great day.